Hello and welcome to this video on stereochemistry. Stereochemistry is a key element of isomers. In particular, it is the underlying element that defines conformational isomers. That is, compounds with the same chemical formula and structure, but not orientation. These are called stereoisomers. It means you get the same connections between parts, but the final structure is different. Stereoisomers are an important part of chemistry and biochemistry. The reality of the world is that as these molecules get bigger, the orientation of molecules becomes increasingly important. Many examples of this are lock and key models for enzymes and proteins, in which something that does not conform in the correct shape will not fit into the receptor or other system. The point on which many of these molecules pivot is called the Stereocenter, and it is the point around which all of these isomers are based. It is nearly always a carbon. In large molecules, this can be one or more carbons around which other molecules move. As a rule, one of the conformations will be favored because it is more stable than the others with a lower energy state. Stereoisomers fall under the wider category of optical isomers. That is, they are visually similar and can be overlaid with more than less complete overlap. The exact overlap begins to vary as you get further into stereoisomer trees, with more areas matching, but the specific details differing to a greater and wider degree. This concept extends a little further with what are known as cis and trans isomers. These have been changed in modern chemistry texts to be Z and E isomers. The Z stands for Zusammen and the E for Entigen. These are the German words for together and apart. This should give you some idea of the purpose of this designation. The arms of the compound rotate on an axis, and if they are on the same side, it is a Z isomer. If they are on the opposite sides or apart, it is an E isomer. A common and easily understood example of this is butene. It is a simple 2-carbon molecule. From these carbons, there are 2 hydrogens and 2 methyl groups, one on each carbon. These create an equally distributed structure. It will have either a Z conformation, in which the methyl groups are on the same plane, or an E conformation, in which they are not. Another type of optical isomer are diaster stereoisomers, which are non-mirror image optical isomers. These have a different arrangement around one or more atoms, and some of these atoms will have the same arrangement, but there will often be one that differs drastically from the other molecules that are related to it. These molecules are not mirror images, and whilst they are partially superimposable, they do not match perfectly no matter how you rotate or flip the image as a whole. Epimers are a subgroup of these stereoisomers, and much like the larger group, they differ at only one location. All epimers are diastereomers, but not diastereomers are epimers. There is a different arrangement around just one atom in the case of the epimer, whereas the diastereomer can have one or more that will change. An example of this is in medicine, and a perfect example within medicine is thalidomide. Thalidomide was a common medication in the mid-20th century. It was prescribed to women who experienced morning sickness. There is an R positive thalidomide formula and an S negative thalidomide formula. The positive form is a mild sedative. The negative form is a potent phocomelia agent that causes severe birth defects in the long bones. The positive icon in naming indicates that the molecule has a property in which light shone at it bends to the right. This is represented by the term dextrorotary, D, or a positive sign. The opposite is when the light turns to the left and is called levorotary, L, or a negative sign. The difference is in whether or not the nitrogen is bonded with a carbon structure and that this bends the light left or right. This reflects the stereochemistry of the molecule and whether or not the stereocenter is symmetrical or asymmetrical. A more complex example is menthol. It has 3 stereocenters. The first is on the left and is responsible for what is generally considered the classic menthol flavor. The one on the right is almost identical in its properties, but carries a far less potent taste. Because of these 2 stereocenters alone, menthol has up to 8 possible conformations. For most people, the relevant molecule of interest is something like glucose, and that has been described previously. For everyone else, stereochemistry is important in chemistry and biochemistry. As in the case with thalidomide, it can be the difference between an effective medicine or one that causes mass harm. When you want to synthesize a drug or compound, knowing the stereochemistry is essential to ensure you not only get enough in your yield, but that you are yielding the right substance. Thank you for watching this video. If you have found it interesting or useful, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions below.